different therapies of different targets, combinational therapy for aging in general. It's been a focus for us for like half a year maybe already. But we have different projects that we so for longevity. I will just like briefly name them to you, and then I would like to maybe ask you several questions, and I'm sure you will have a lot to talk about.
Great.
Yeah, so first of all, we're writing a review right now. We're trying to set like the basis of how the future combinations should be selected, like using what principles, because there could be different, like should we choose like all the polymers of aging and put them together? Should we take like a very, very potent therapy and then try to balance its side effects, which will obviously will face, or should we like do some other approach there? So this is what we're trying to do right now, and probably this will be a number of articles. And I think this is something that the industry should have done quite long ago. We obviously need to not only try to compound by compound, and you're not the person that I have to explain it to. Obviously, it's probably for our viewers right now. So yeah, if we have the ability to additive effect and synergetic effect, let's try the combinations for sure. So yeah, and also we have like a huge group chat, like a forum dedicated specifically for that topic. So different groups of ours are trying to address this issue from different angles. We've built a database, open genes database of genes associated with aging and longevity. And this could be a potential tool to select like the base target and probably therapy as well. And this is a combination approach again. And the other angle could be like mathematical approach, just work with a bunch of data, and this will be like a completely different thing here. And I hopefully another Anastasia of ours from our team, Anastasia Velikanova, will soon join us and probably ask some questions later too. So yeah, here's what we do, and we actually are testing the one combination at the moment on flies in a lab in Turkey. We just like creating genetically altered creatures and see like what combination of genes would actually give the effect, the needed effect, the life extended effect, obviously. And hopefully we'll start another experiment soon in New York. But this is what we do. Your experiment is fantastic too. It describes exactly the approach what we think should be done years ago. But from what I've seen, like I read the article by Arkady and his colleagues, you selected 4 therapies, and it seems like you just like took the best of them. We have the best thing, here. Obviously, yes, there are the best candidates to be tested first, but afterwards, as I understand it, you want to scale the project and probably test some other compounds in other combinations. What would be your approach to select the best combinations? What would be like the theoretical principles behind it?
Yeah. All right. So, okay, let me give a long answer because there are quite a lot of things to cover that feed into this. And of course, some of what I want to say applies more to my group than it does to other groups. A lot of it comes down to how expensive the experiment is. Let's be very clear about that. Well, first of all, there is a question of what species to use. And as you say, there's some considerable argument for doing work with fruit flies because we have a great deal of information about the aging of flies, and it's much less expensive to do experiments in flies than in mammals, in mice. Of course, for me, the focus is always to look at the whole community, to look at the experiments that everyone is doing and try to get the most total impact from everybody put together. And of course, that requires a lot of communication between the various groups that are doing things. And I'm in a good position to provide that communication. So let's talk about flies first of all. At the moment, I am already in communication with two groups who are very interested in doing more work in this kind of area, combination therapies in flies, and who are very rigorous and experienced and so on. So there's one group which you've probably heard of. So I'm sure you know who Michael Rose is, the originator of this whole field, really, in fruit flies. He created a company called Genescient some time back. It's been a bit of a clusterfuck, to be honest, because there's a lot of personalities that would find it difficult to work with each other and all that. But anyway, the long and short of it is that at the moment, that work is mostly in the hands of someone who is very easy to work with, Ben Goertzel, who, of course, made his name in artificial intelligence, artificial general intelligence, but he's been putting a lot of effort into longevity over the past several years, and he has basically licensed the intellectual property from Genescient, and he's working with that, both in the sense of analyzing data and also doing new experiments. Now, what Genescient have been focused on, even though their extremely long-lived flies were obtained by many generations of selection, and therefore they obviously have a genetic basis for their longevity, nevertheless, what he's interested in is identifying drugs, compounds, that can achieve the same effect. And of course, the way that they're going about that is by looking at the gene expression profiles of these long-lived flies, comparing them with the normal flies, and figuring out, what genes are suppressed, what genes are upregulated, and finding compounds that can partially, anyway, mimic that. And that's definitely an exciting way to go, and it may be more powerful than doing what you just said that you're doing in Turkey, taking actual mutants and changing them and combining them. Firstly, because you will be closer to the clinic. If there are actual small molecules that might be druggable, might be possible to give to people or to mice, then that's closer. The other reason is that there may be a greater fidelity, actually. You may be able to have effects on the expression of multiple genes with one compound that will kind of mimic what has been done with multiple mutations in these selected flies. That's just a guess, though. That's just speculation, that last part. Anyway, though, the point is they're doing very useful work, and they are, I believe, very open to collaboration with other groups. So I believe that it would definitely be valuable for you to talk to Ben about this. The other group that I think should be involved much more in this is not really a group, it's just one guy. His name is Robin Mockett, Mockett. And not many people know Robin, but that's a bad thing, because he's brilliant. He is originally British, actually, but he is a professor in Alabama in the US, and he's about my age. Really, I would say that you could call him the most rigorous fruit fly gerontologist in the world. He has a spectacular track record of getting extremely reproducible results and understanding, what he's doing better than anybody. And he's basically got no funding at all. Because fruit fly work is so inexpensive, he has been able to do small-scale experiments just by funding them out of his salary, just because he's a professor and he teaches and so on. But he doesn't have any grant funding. So I believe that he is being very underutilized. and it would be extremely valuable to change that. Okay, so that's pretty much all I want to say about fruit flies for the moment. But of course, there's the potential to bring other groups in here.
Mike Rose.
I'm sorry?
So Mike Rose.
Yeah, there's not really any point in speaking to, yeah, there's not really much point in speaking to Michael Rose himself at this point, because, as I say, the technology has been licensed to Ben's group. So Ben's the person you need to talk to there. And I can obviously introduce you.
Yeah, we have a group chat together.
Yeah. And there may be other groups in the fruit fly world that are worth doing, but we'll worry about that later. Now, one thing that I should probably mention is that a paper came out last week that has made a big splash that's all about how untranslatable fruit fly and nematode work is to mammals. And it's probably an exaggeration because so few compounds have been tested in multiple animals anyway. But the main reason why it's probably an exaggeration is because of dosage. In general, because mouse experiments are expensive, you get very few experiments where they test multiple doses of a life-extending compound or whatever. And even in flies and worms, there's not nearly enough of that. So a huge need right now, I believe, is for bigger fruit fly experiments that can test multiple doses of multiple things. There is there's a nice fact here, which is that statistically, you can get away with relatively small sample sizes for these experiments, just by assuming that the dose response curve for any given compound is going to be a smooth curve. Like there's going to be a point where it starts to be toxic, but it's going to be like, a U-shaped curve rather than some kind of, wiggly thing that goes all over the place. That's a very safe assumption. And if you make that assumption, then you can cut some big corners on the effects. So I think that the person that you should probably talk to who would be most valuable about that is Aubrey De Gray, who you may know. He's a statistician based in Paris. He has a full-time job working in a bank or something like that, but he does longevity work in his spare time, including his own mouse experiments. But the point is, he understands the statistics of all of this very well. He has also explored this in depth with Josh Mitteldorf, who is another statistician, mathematician who understands this kind of thing better than I do, to be honest. So I would talk to Aubrey. Aubrey is easier to talk to than Josh. So that's another thing to look at, especially if you think that you want you might want to do bigger fly experiments than what you've done so far. I know I haven't said anything yet about which things to bring in. I'll come back to that in a minute.
Right.
But first of all, let me talk about mice. So mouse experiments are ridiculously expensive, and a huge amount of the experiments that obviously should have been done in the past and have not been done, the reason they haven't been done is because nobody could get the money. It's just a fact. And I'm talking about really good people. I was just having a conversation with Matt Kaberlein about this. He's about as mainstream as you get. He was talking about grants that he couldn't get funded for doing very valuable work. So it's miserable. But of course, we are in a somewhat different world now. We have billionaires giving money to expensive experiments. And so the right thing for people like me to do is to figure out how to spend that money well. And at the moment, there are various ways in which one could go about that. So Brian Kennedy in Singapore and his group, Andrew Meyer and so on, they are putting together a big combination study, and they're looking at supplements and other things that don't need to be approved by the FDA, or they've already been approved by the FDA and so on. That's the main thing that they're looking at, because they're interested in moving to humans as quickly as they can. And that's fine. And they are very approachable. They are very happy to talk to other people, and to give advice, and they're very knowledgeable people, so their advice is valuable. Um, and I can certainly introduce you to them if you want. But yes, as I say, they are focusing on that kind of intervention, whereas we are being courageous and looking at genuine damage repair interventions. The difference, of course, is that most of our interventions need to be injected, as opposed to being put into the diet. And that's really a large part of why they're more expensive. Another large part is that the things we inject, it's just expensive to make them. So, for example, one of our interventions involves injecting young blood stem cells into old mice, right? So this is a kind of variation on parabiosis. Rather than looking at the plasma, we're looking at the cells. And the reason we're doing it is because other people have obtained very good lifespan results this way. But it takes $500,000 to make enough stem cells. I mean, it's a hell of a lot of money. It's just like most people just couldn't afford it. Similarly, we are using telomerase gene therapy. We are injecting telomerase. That costs, well, we actually are still exploring two different ways to do that, but it's definitely going to cost $300,000 or $400,000, one way or another, just to create and make and grow enough virus to be able to do this. It's terrifying. The senolytic that we're making is going to cost us maybe $100,000. Even the rapamycin that we're putting in the diet, it has to, of course, people have done a lot of experiments on rapamycin, and so we have a pretty good idea about what works best. And there's this way of putting it into little microcapsules, little microscopic capsules, which seems to be the right way to go. But that costs quite a lot as well. We're having that manufactured right now. So yeah, I mean, and all the labor involved is also, very significant. So, of course, we're not just doing lifespan experiments. Especially with mice, it's really important to do health experiments as well, and to measure, how these mice are getting on. And some of that is relatively quick and easy to do, like you take photographs of the mice so that you can measure their level of loss of hair, for example, alopecia, or you can measure the bending of the spine, the kyphosis. But some of the experiments are behavioral. You have to do things like measuring their memory, and these are labor intensive. So, the experiment, this first experiment we're doing with 4 interventions, not even playing with dosages of anything, just a particular dose, right? It's costing us $3 million total, right? And so I'm out there, of course, doing what I do and trying to persuade people to give us more money so that we can do the same thing again, starting in probably October if we get the money. I'm fairly optimistic because people do seem to like what we're doing and they understand the value of it. But nobody else is even thinking about doing experiments like this. The Buck Institute were thinking about doing fairly ambitious experiments. But I don't know if you've heard about this, but I think it's an open secret now, that their money went away. There was one guy, a very wealthy crypto guy, who promised the Buck Institute $70 million, paid as $10 million per year for 7 years. And he paid the first 10 million and they got going. And then he looked more closely at how they were spending the money, and he was disgusted at the level of overheads and indirect costs. And Eric Verdon didn't want to take a 50% salary cut, that kind of thing. So basically the guy said, right, you can keep your first 10 million, but you're not getting any more. So the project is now on hold. I mean, pending they're getting alternative funding from somewhere else. Good luck with that.
Was the
But
funding some exact experiment or
yeah, so
talk in
basically,
general?
again, it was an experiment a bit like, but what rather like what Brian and his group are doing in Singapore. So yes, it was uh, everything would be in the diet rather than by injections. But yes, it would be same as our experiment, same as Brian's. It would be in late onset, so starting at maybe 18 months old mice, right? And um, and combining things, yes. So basically, same kind of experiment as Brian's, really, but it looks like it's not going to happen. And then, of course, there are other groups who are thinking about this. I'm sure you've spoken to Alexei Moskolov and Ivan Morganov. They want to do similar work, but they don't have much money yet either. So yeah, I mean, we
Yeah.
basically.
I haven't had a strategy with the mice just recently.
Uh-huh. So basically, the main thing I want to do at the moment is bring money into this, not just for my own work, our own work at LEV Foundation, but for everybody who wants to do experiments like this, especially the mouse ones because they're the expensive ones. And I've got various strategies for doing that. One of them, of course, is talking to the crypto billionaires who have been so generous in the past couple of years in the field overall. The other one is Hevolution. So as you know, Hevolution has a chief science officer, Felipe Sierra, who used to run the Division of Aging Biology at the NIA. And of course, the NIA have been doing mouse lifespan experiments for nearly 20 years, the intervention testing program. Now, the intervention testing program has always been criminally underambitious, especially not doing late onset experiments, despite the fact that they accidentally found that rapamycin worked. I mean, it's horrifying how unable they were to actually be at all courageous there. But, of course, this means that Felipe has a very good understanding of all of this, and he understands the shortcomings as well. Felipe himself is a very forward-looking, progressive guy, even though he's like 75 years old. So, so I'm already in discussion with him about the possibility that Hevolution might support a consortium of groups doing this kind of work. And that discussion is only at the very beginning so far, only at square one, so it's going to be a while before it leads to anything, but I'm reasonably optimistic. All right, so finally I want to talk about the choice of what interventions to use, right? So, of course, I've already said one thing, which is that you've got the choice of either doing stuff that's only in the diet, which is relatively inexpensive, but relatively limited in terms of well, I think it's limited in terms of what you would expect to achieve, because it's not really repairing any damage. Or you can do it the courageous way that we're doing, and put in a lot of injections and so on, but then, it's much more laborious and expensive. I believe that we, if doing the courageous approach, have still got a lot of choices out there of things to use. The four things that we chose this time, as you said at the beginning, they are ones which already are looking like they are the best. In other words, individually, they have been shown by other groups in published peer-reviewed work to extend mean and maximum lifespan in mice when begun in middle age, at the same kind of age that we're beginning, right? And of course, the magnitude of that effect is, it needs to be statistically significant, but that's really all I'm looking for in order to justify putting these things together. Of course, one other thing that's important is when you're doing damage repair or anything like that, to try to repair different types of damage with each of the therapies. So we're trying to, take treatments that are likely to be very different from each other in terms of what impact they have. But still, we've got lots of things left. Like, for example, this time, our senolytic is a small molecule. Senolytics have a terrible track record of reproducibility. The one we're using is probably the best, galactose conjugated navitoclax. But still, we want to do something that's more of a genetic approach. So we're already talking to Matt Schultz at Oshin about doing something with his constructs to deliver genes for killing cells that express a high P16 or whatever, as in the second round. We haven't committed to doing that. We haven't made final decisions about the second round at all yet, but that's one of the things we're exploring. Similarly, we'd like to do plasma exchange or neutral blood exchange, which of course is very exciting. In a lot of people are doing great work there, and at the moment, we're doing this other thing with blood stem cells, but it makes definite sense to try and do the albumin thing as well. And so on. We've got lots of other ways. We may very well do partial reprogramming one way or another. We're not quite sure how we're going to do it, but again, there are various options. Of course, lots of people are working on that, and sometime around April or May, we will decide what is the most promising one to use. So that's the kind of way that we're doing it.
And you're quite cautious about reprogramming, right, as far as I see, right?
I am fairly cautious about its safety in humans, but I'm pretty happy with how things are going in mice. The main reason I'm cautious about its safety in humans is cancer, as I've explained.
Obviously.
And the thing is that if it is bad if it promotes cancer, then the way it's going to promote it will be by turning precancerous cells into properly cancerous cells. And of course, it will take a long time for those cells to get to the point of being a clinically detectable cancer. That's why we can't trust the mouse experiments. Mice just don't live long enough for that. Mice die of cancer a lot, as you know, but the cancers that they die of are cancers that began very early in the mouse lifespan, right? So we can't really do that experiment in mice. But yes, as I say, I'm not really worried about that when we come to mice for two reasons. Firstly, just getting things going in mice has its own publicity value. If we can show that we can greatly extend mouse lifespan with late onset interventions, then it becomes so much easier, it becomes so much more difficult for deathist people to say, aging is not a disease and it's woven into the fabric of the universe and, it's like gravity and we'll never be able to use medicine against it. You can't say that anymore. That's helpful. The other thing, of course, is that we may very well bring cancer under really good control. As you know, I'm very fond of various technologies involving telomere control, especially the one that's being pursued by Maya Biotechnologies, this drug called 6-thiodeoxyguanine. And, of course, immunotherapy against cancer is also still progressing rapidly. So it's very possible that we will bring cancer in humans under sufficient control in the next decade, that we will be able to play fast and loose with, things like partial reprogramming and get away with making more cancer.
Mm-hmm.
All right, so yeah, I'm doing all that. But so let me finish by talking about how I would make choices when it comes to dietary stuff in the diet, because that's obviously what most people are doing, and it's largely what you're going to be doing. I think there, again, we need to try to identify things which seem like they would be affecting different types of aging, different aspects of aging. But we have to start from acknowledging that what we're going to be doing is slowing aging down rather than reversing it. We're going to be making metabolism run more cleanly in one way or another, rather than eliminating damage that's already happened. So there are not many examples where this has already been shown. The best one I know is rapamycin and acarbose, which were used in mice together, and it looks like they're acting pretty much independently. But not nearly enough experiments of that sort have been done. And since you're doing work in flies as well, I think that there's ample opportunity to get much more data on of that kind, to find out which things really are different. The thing is, if you're manipulating metabolism using dietary things, then it's just complete guesswork whether things really are acting independently. Brian Kennedy has actually highlighted very strongly over the past year or so that it's complete guesswork whether two compounds are going to antagonize each other and actually neutralize each other's benefit. right? It's just, whereas with damage repair, you're much less likely to get that kind of thing. You might get it, and we're doing it. We've designed our experiment to detect it if we do get it, but we don't expect it to happen very often. So yeah, so really, a lot of it is, everything that's got some kind of evidence in lifespan, even if it's in flies or well, not worms. Okay, let me say something about worms. The fundamental problem that I have with worm lifespan stuff is that it's just too easy to get a 30% increase in lifespan. There are hundreds and hundreds of ways to do it. And that tells me that we are just very bad at the controls, at growing worms in a manner that makes them happy. That essentially we're poisoning them, and most of the things that we do to extend their lives are just like weakening the poison. Now, of course, people who actually work with worms would be horrified at this, at me saying such a thing. But yeah, I mean, I think at the moment we have to be very careful about stuff that looks promising in worms until it also looks promising in other species. The only exception, I would say, is if something gives a really big increase in worms. If you're up around 70 or 80% increase in lifespan, then I'm interested. But if you're around 30%, I'm not interested.
Yeah, all right. But going back to cancer, what do you think about possible impulse therapy? Because and also it's for another reason, really two reasons to do that. First is we have a risk of growing cancerous cells, and so we could be given, I don't know, VGF plus I don't know, inhibit growth factors at the same time, or doing this periodically. Or there's another issue there. It seems like our body, human body, is kind of resilient. It's very resilient. It's very hard to affect it in a good way and in a bad way also. So probably if we want to affect aging, there has to be something very, very strong, almost toxic, to push us out of this balance, our balance, which is taking us into aging state. But then we will have to balance it with something else, or give it for a short period of time.
All right. Well, I didn't really understand the first part of what you said about cancer, so let's come back to that in a minute. But let me answer the second part. So I think what you are describing as resilience or resistance to being changed is not really correct. It's only correct when we talk about calorie restriction and things like it, calorie restriction mimetics. The reason I'm saying that is, I guess you know that 20 years ago or so I published an explanation for why calorie restriction itself works so much less well in long-lived species than it does in short-lived species. It's just a very simple consequence of evolutionary gerontology. It's basically just because famines in the real world, in the wild where evolution happens, long famines do not happen as often as short famines. And in particular, long famines do not happen often enough to deliver the selective pressure to evolve or maintain metabolic responses to them. So basically, every species gets more or less the same absolute amount of increase in lifespan from calorie restriction when you do it right, as opposed to the same proportional amount relative to their natural lifespan. That's an approximation, of course, but it's not far off. And the same applies to calorie restriction mimetics, because, of course, what a calorie restriction mimetic is it's a drug that tricks the body into thinking it's in a famine when it isn't, which means it turns on the same responses, the same changes in gene expression profile that famine itself does. And that means that you're going to get the same kind of, at most, the same kind of magnitude of response. You're never going to get a CR mimetic that does more than CR itself does. And at the moment, rapamycin, when done right, appears to get roughly as much as CR itself does, starting at a given age, right? But and most things don't get that much, but certainly nothing gets more. And I would put good money that nobody will ever get more out of a CR mimetic than what they can get out of CR itself in any species starting at a given time. So, of course, that's just one part of the resilience and resistance to being knocked about that you talk about, but it's actually the central one. People. I mean, there are various things that are really important to the body to keep right. The famous experiment that was done about a century ago by Haldane, very famous biologist in the UK. He was crazy. He was completely crazy, and he used to do the kind of self-experimentation that would put Liz Parrish in the shade. He tried to change the pH of his blood, right? And he succeeded in changing it by a whole unit. I can't remember which direction. But he only succeeded in changing it by a whole unit for 1 minute. And even that made him very sick. So don't do that. The pH of the blood is something that is what it is, and it's stable for a reason. But all of this that you're correctly saying, this resilience, only applies to metabolism. It applies to the stuff that the body is constantly doing to keep itself alive and in the best position to pass on genetic information and so on. It doesn't apply to damage. Damage, remember, accumulates throughout life. And it's basically harmless until middle age or later, because the body is set up to tolerate a certain amount of that damage, just in the same way that your kitchen is set up to tolerate a week's worth of garbage, but not a month's worth, right? So if you remove damage, then you're not actually butting up. You're not actually trying to oppose the body's resilience. You are in fact augmenting the body's resilience, so putting it back into the more resilient state that it was at an earlier age when it had less damage and it was carrying around. So that
makes total sense. It makes total sense from a biological or physiological point of view. But have you read Peter Fedichev's works in Gero? They're talking a lot about it. What do you think about that?
Yeah, sure. So yeah, I mean, so first of all, I do not claim to understand Peter's work in detail. I've tried, and it's quite tough. But I do think that it's basically correct. However, I don't think it really challenges what I'm saying. It really just it's a way of discriminating between the effects of different types of damage, kind of where the different types of damage fit in the causal network of events, if you like. And that's very useful, but it doesn't really change anything I just said. Still, if you can just repair all the damage and put the body back into having the same structure and composition, or more or less the same structure and composition that it had at a younger age, then it's also going to have the same function, and it's also going to have the same remaining healthy lifespan.
All right, but to clarify what I was meaning about the cancer cells, obviously some effective therapies can be very oncogenic. So we can just give something periodically, affect I don't know, give VGF, growth factors, and then stop ourselves and inhibit this. So maybe
Aubrey,
we should do this like this.
yeah, may I also ask, hello, I'm
Sure.
Timothy Glinin. It's just maybe a question about how you perform experiments with rapamycin. Would you like to perform a whole period of live treatment, or just a periodically treatment of rapamycin?
Yeah, so we thought about this. Of course, there's been a lot of rapamycin experiments done with different doses, different starting times, and also, as you say, there have been a few experiments done in which rapamycin was given for only a short amount of time and then it was discontinued. So we had to choose one approach. And so what we're doing is we're starting at 18 months and we're giving this, we're giving it for the rest of the life. But, we just had to choose one, really. So I'm not saying that there's anything particularly wrong with doing short-term stuff. Right, coming back to Anastasia and cancer. Oh, and Didier and various people want to ask questions, and I'm totally here for it. I have another hour if you guys want me. I can
Yeah, great.
there's lots of you, so this is a good use of my time, right? Right, so cancer. So I mean, for the longest time, people have understood, even though they don't necessarily say it, that aging is basically a war between cancer and everything else. It's a trade-off between the two. In other words, an enormous amount of the work that the body already naturally does to prevent it from dying of cancer before we have reproduced has downsides in terms of limiting our regenerative capacity in various ways. And so we absolutely need to break that trade-off. And this was part of what led to the original sense classification back in 2000. And people generally agree about this. The question is how to break the trade-off. And of course, one way is to really cure cancer, and then you're done. You can be fast and loose with regeneration. The other way is to somehow compensate for the lack of regeneration in a way that doesn't cause cancer. And that's really, really hard, but it's basically what Mike West at Ajax is trying to do. You're trying to identify different factors, not the Yamanaka factors, that will restore regenerative potential without taking cells so far back as to make them pluripotent and therefore more likely to be cancerous. But that's at a very, very early stage right now. I don't really yet have any reason to be confident that that's going to yield good results soon. Yeah, I mean, so I mean, I'm sure you know that I have been working very hard to promote and to bring money to this company, Maya Biotechnologies, which is pursuing this drug thiodeoxyguanine, because I believe that it is by far the most promising single treatment for human cancers that's being developed right now, by far. And then, as I mentioned, cancer immunotherapy, that's still moving forward. One of the other companies that I have worked very hard to help and promote, and it's doing really well, is Nanotics, Lou Hawthorne's company. There's very good reason now, I believe, to feel that that's the missing link in cancer immunotherapy, that by using that kind of technology to soak up the cloaking that cancers use to prevent themselves from being attacked by the immune system, you can make cancer immunotherapy much more powerful than it otherwise is. And Lou has got now really good collaborations with big clinics like the Mayo Clinic, Cleveland Clinic. It's really fantastic how well that company is doing. So I think we can be hopeful. I'm not saying we can be confident, but we can be hopeful that cancer really will be brought under sufficient control fairly soon that we can be more liberal about regenerative therapies like stem cells and so on.
Right. I will just have like one question, and then Stanis, I will gladly give you the ability to ask yours. So probably the major question here is how do we scale the whole project? Obviously, we need to test much more. So your budget, well, your estimations are 3 million, and it's like 1 million is going only to produce the compounds, right? Something like that.
It's about that. It's about that. Let me think now. It's probably more actually. It's probably certainly between 1 and 1.5. Yes. And the mice themselves cost like 350,000 because we buy them when they're already 18 months old, right? And the people we buy them from have had to keep them alive all that time. And then keeping them alive during the experiment, obviously that costs money. All of the labor involved in doing the health span experiments costs a lot of money. So yeah, I mean, we've worked really hard, and ICOR have been fantastic to work with because they're very, they're very immortalist too, right? So we have worked really hard to keep the prices down. If we'd done it with any other group, it would have cost 5 million.
So how do we scale it? What could be the potential places like
Yeah, well,
costs?
so there's two answers to that, right? Number one is do everything in flies, and number two is find some very rich people and persuade them to give you money.
No, actually, I agree that mice are more, like effective in persuading people. Yeah, it's better to show the result, obviously. But I don't know, like maybe, obviously, when we move to the next compounds, the prices for the compounds themselves will differ. They could be cheaper, they could be much more expensive because, I don't know, we could decide to go into liver transplantation for each of these creatures. Who knows how much that will cost. Yeah, but if we grow the number of animals, does it make them cheaper, like per mouse or per rat?
If you use more mice, does it make it cheaper per mouse? Not really, no. Not much anyway. I mean, there are probably a few things which have a little bit of economy of scale, but no, mostly it scales with the number of mice, I'm afraid.
Oh, so no answer, just like let's fundraise better.
Yeah.
Okay, I will think about it while we give some people the chance to speak to. So, Status, what was your question if we haven't answered it already?
Hi, my name is Stanis. I'm a postdoc from Albert Einstein College of Medicine. I actually have lots of questions. I don't know. So maybe I would start with the technical questions. So you told that you decided to use the whole experiment treatment with erythromycin. And how do you plan to overcome its side effects? Because,
yeah, we're not actually too worried about the side effects. And that's simply because, of course, first of all, let me ask you, when you say side effects, do you mean the side effects that are talked about in humans or side effects in mice?
Of course, side effects in mice, because the majority of side effects in human, they are self-reported, and mice cannot, complain about all these things that people complain about. Yeah, so I'm actually most of all worried about the glucose intolerance that is developed.
Glucose intolerance, yeah. Yeah, so we will be measuring that. That's one of the things we'll be measuring in the blood draws that we take throughout the thing. But at the moment, our main priority has been to do as closely as possible the same thing that other groups have done that obtained good lifespan results. That we're basically saying, well, okay, yeah, maybe we know about side effects, maybe we know about other limitations that might motivate doing something different than what the previous study did, but let's start by just replicating the previous study and then combining it with other studies. So in our study, we have 10 different groups of mice. Obviously, we have a control group that's not getting anything, and we have a group that's getting everything. But we also have 4 groups that are each getting just one of the interventions as a baseline, to replicate the previous work that was done. And we would not, and we feel that it's important to maximize our chances of replicating the previous work, which means that we're changing the protocols as little as possible. The other 4 groups that I haven't mentioned yet are the groups that are being used to identify antagonistic interactions, where we basically do all but one of the 4 therapies. So we've got 4 of those groups as well.
And about the blood stem cells transplantation, so do you plan to do it once, or you want to repeat it? And if you want to repeat it, how you would understand, so which criteria you will choose to understand that, okay, so the beneficial effect is now finished, we need to repeat the injection, the transplantation. How do you plan to do this?
Yeah, so I think that's a great question. So the blood stem cell transplantation is the most expensive of the interventions that we're doing. So we have had to cut some corners there in designing what we're going to do. The main study that we are following that led us to do this came out, I think, 3 years ago now, and they actually did 8 rounds of hSC injection on the mice whose lifespan they measured. But conveniently, they did also measure the percent engraftment of their cells after each one of these injections. So we have a pretty good idea of how much we can get based on injecting a certain number of cells each time. And the compromise that we have made is that initially we're going to have 1 round of injection, but we're going to inject twice as many cells per recipient mice than what this paper did. So we're hoping that we'll get something like maybe 30 or 40% engraftment. Well, this is measured as percentage of the total number of cells in the bone marrow. So in other words, when you look later on at which type of stem cell the cells in the actual bloodstream came from, you ask for that proportion, right? And we need to wait 3 months to do that, because we want to make sure that we are seeing the progeny of long-term repopulating cells, right? So we're going to wait those 3 months, and we're going to see what the proportion is. And if we think that it's not enough, if we believe that we haven't done enough, then we'll do a second round at that time.
And the cells, so who will be the donor of the cells? It will be the same mice, or it will be some other mice?
Same. Well, okay, actually, great. So, in general, it will be the same strain. We're using C57 Black 6 for the experiment, right? So, of course, we're taking the blood stem cells from young mice because that's the point, right? And that's what the previous paper did from 2020. But yes, we are using the same strain, almost. We are actually using the CD45 allele difference to identify the percent engraftment, but we're not actually going to use cells that are all from the other allele. We're only going to have a kind of 1/10 of our donor cells are going to be from there, because that's enough to be within the level of detection. And it turns out that those mice are considerably more expensive, so we saved a couple of $100K that way.
Okay. So now I have more philosophical questions. So you talked very interesting about that. So the beneficial effect, life-spanning effect of any mimetics of caloric restriction have no possibility to overcome like 30–40% of lifespan increase. And so on the one hand, it looks, really convincing, because the, mTOR signaling, is very diverse, and it has lots of, feedbacks, negative, positive, and it looks like very, there is sustained, signaling hub. But so what we are trying to do in our experiment, so we want to, in addition to so we're actually going to use everolimus, because it's more cheap, a little bit cheaper than rapamycin. But in general, I believe that it should be, very close. And we also want to combine it with some other compounds that should act downstream of mTOR on some other, some other touches that we think that we really need, like we are going to use sulforaphane to increase the amount of NRF2. We're going to use spermidine, nobility, and so on. And so of course, it's so we're also, they're limited in our budget, much more limited than you. So we have only 15K. So it's like, it's really like, the shoot in the dark, with this money. But still, so we believe that at least we can try to do to overcome these, self-regulation of mTOR by acting downstream. So what do you think about these possibilities that we can, like, trick these mTOR network?
I mean, I think it's a worthwhile experiment to do, but if you ask me to guess what the result will be, my intuition is you won't have much benefit over and above using rapamycin itself, simply because these downstream pathways that you're talking about have also evolved to do what the what evolution wants, and so if you try to disrupt them, then I think, if anything, you're more likely to end up reducing the initial effect of the mTOR inhibitor than increasing it. But I could be wrong. So I applaud your idea of doing the experiment.
Okay. And so, yeah, the last question. So, yeah, mostly like social economy, related to social and economist things. So I will start with flies and mice. Yeah, I totally agree with you that with the flies, it's working flies is much more expensive, and you can test lots of drugs, you can test lots of concentration, you can test lots of dosing regimes and so on. But so you still cannot go directly from the flies to the clinical studies. So
Right.
you still need to confirm your results in mice.
Right.
And also, yeah, for example, you can find, for example, a good combination. But for example, the dosing, so you still have to redo it again in the mice, because so there is very difficult to translate the dosing regime from the mice that have totally different digestive system to the mice. And so the question is, maybe the experiments in the flies are redundant, because so if you still
so no, I don't think they're redundant. First of all, even though you're absolutely right that the results in flies could not be directly replicated with certainty, that the optimum combination or relative dose in flies would be the same, nevertheless it probably narrows the variance a bit. You probably have a somewhat better idea of what the optimum dose or the optimum relative dose is going to be. Even if it's only a bit, it's better than nothing. But the other reason why it's not redundant is because there will be some people with lots of money to spend who will be tipped over the edge. You have to remember that for every person who is giving money to this field, there are 10 people who are nearly giving money. They're just waiting to be tipped to jump off the fence, right? And we only need a few of them. So those are the people that I've been focusing on for the past 20 years with occasional success. That's the way to think. Those are the real audience right now.
Okay. Do you think that there is a possibility that we can, for example, discuss some treatments, some drug, because described from our attention, because it did not show any effect in the flies, but it will have the effect in the mammals, because there is definitely very big evolutionary distance between these species, and so it's another way to ask if fly experiments are redundant. So because
of course that's going to happen sometimes, and there are certainly some treatments in mice that you physically can't do in flies, like you can't do stem cell therapies in flies, right? Not really. So yeah, of course there are those differences, but again, I think those problems are not enough to justify simply abandoning all fly work. I think we've got enough chance with very much less money to move the needle with a few people, and get a lot more money in the door to do the really expensive experiments in mice.
I would like to give the word, Stanis, I would like to give the word to the next guest here. Didier was waiting for quite a long time. So Didier, would you like to ask your questions?
Yeah, hello.
Well, I think Nastya was before me asking especially, but okay, I will take the chance. Sorry. Oh no, I give the word to Nastya first.
Okay, Nastya first then.
Yeah. Hello. Thank you for the interesting talk. And I have two questions. The first one is how are you going to estimate the results? For example, are you planning to apply some modern algorithms like in Peter Fedishev's works to count biomarkers of aging and how it changes during your experiment on group? And maybe you could also track animals and use tracking data and apply some AI algorithms to it. And
Right. Yeah. Okay. So let me deal with that. So we're not going to get as sophisticated as Peter on this. We simply don't have the money to do large numbers of biomarker studies, but we're doing as many as we can in different ways, as I mentioned during my early remarks. You know, we're doing visual stuff, we're doing behavioral stuff, we're doing blood draws, we're doing histology of organs on some of the mice that we kill. But we're doing it pretty much the traditional way. But one thing we are doing differently that I don't think anyone's done before is that when we make these measurements, we are not choosing the time, the age of the measurements as the same age across all the groups. Most people say, okay, well, we're doing this experiment starting at 18 months, we're going to measure everything that we want to measure, we're going to measure it at 21 months and 24 months and 27 months. We're not doing that. What we're doing instead is we're choosing the time points for each group individually, separately. So we've basically got 20 groups because we've got 10 different treatment regimes and we've got males and females. Within each of those 20 groups, we are going to do our measurements when 10 of the 50 mice have died. That's the first time point. And then we'll do it again when another 8 of them have died, and so on. So this means that we will be factoring out the lifespan effect of the therapies. And we believe that in this way we'll get a much better signal-to-noise ratio. We'll basically be able to see which therapies are having more effect on which types of aging, which types of life-threatening problem, and which ones are having less effect. Because you know, if you do it the normal way, you have a lot less of a signal because you're masking it with this other thing that you already know is highly correlated with everything you're measuring, namely lifespan. So this is an innovation that I thought of, and everyone seems to like it. But that's the only really clever thing we're doing.
Maybe you also could make continuous tracking with video recordings, because we tried to do it and it's quite, it is very cheap. Yeah.
I wish, but it's not really very cheap when you've got 1,000 mice. And you know, we've got there are various other things you can do. Like, for example, you have a running wheel in the cage, right? You can measure how much running is done. But unfortunately, that's also very misleading because you don't have just one mouse in each cage. You have maybe 5, right? And there's a dominance effect. So one mouse will do most of the running. Things like that. These experiments are fucking hard. I hate it, you know. But yeah, there's so many things that you can get misled by, and it costs enormous amounts of money to avoid.
Thank you. And the second question is, it is rather hard to choose the distribution in time of a particular intervention, and how was the process in which you have chosen the distributions in time for intervention?
Okay, so there were really 2 things that drove this. First thing is we wanted to start in middle age, not too young, not too old. If you start too young, then first of all, the experiment takes even longer and it's even more expensive. But secondly, it's less relevant to people who pay taxes, right? And who, you know, give money and so on. So we wanted to start in middle age, but no earlier. Then, of course, some people have done the opposite. They've started really late. And recently there have been a few papers where people wait until half the mice are dead, right? And then they get really good results, like they double the remaining lifespan or more. Some people, I think, even treble it. You know, that's fantastic, until you remember that if you're waiting until half the mice are dead, then the mice that are not dead are very unwell. You know, they're definitely going downhill. And the goal of biomedical gerontology is not to keep people alive in a sick state of health, right? So it's kind of answering the wrong question as far as we're concerned. We want to start with mice that are still basically healthy, even though they will be sick fairly soon, and to extend their healthy lifespan. So that's really how we chose that time. Now, the other answer to your question is how we choose the relative time of the various different interventions. And our decision was basically we want to do them all at the same time, with the only caveat that we want to try to anticipate any interactions that they might have. So if you look at the three damage repair interventions, the stem cells and the telomerase and the senolytic, one thing that we thought, well, we don't want to do the telomerase before the senolytic, because the telomerase might kind of desenesce some cells and protect them from the senolytic. We don't want that, right? Then similarly, we thought, well, we don't really want to do the stem cells before the senolytic, because the stem cells may engraft better and generally work better if they're going into an environment that's already had the senescent cells removed, or a lot of them removed. So that's the way we made that decision. We did the senolytic first, and then we're doing the HSCs, and then we're doing the telomerase.
And maybe I missed it. How overall, how much series of interventions are you expecting to do for?
Okay, so the rapamycin will be throughout the lifespan, starting from 18 months. The HSCs we'll do once, and then we'll wait 3 months to see how much engraftment we got, and we might do it a second time. The senolytic we do once, though it's actually given over a period of, I think, a week, something like that. You give multiple injections, but once we've done it, we don't do it again. And then the telomerase, actually, this is still uncertain. We are still working, there are supply chain issues, so we may use CMV, cytomegalovirus, or we may use AAV, adeno-associated virus. And in both cases, there are published studies, and the answer to your question is different between the studies. So with AAV, the way it's been done, that worked, is just to do one injection. And with CMV, the way it's been done, that worked, is to do monthly injections. So we will follow whichever protocol.
Yeah, okay. Thank you so much.
Pleasure.
Yeah.
Okay, great. Let's give the word to Didier then, right?
Yes, first, it's really great, very, very interesting. My question, my two questions will be no surprise to you, Aubrey. It's about the first part is about evolution, Altos Labs and Google Calico. Why is it impossible until now to convince them to use a symbolic for them amount of money, like 10 million, to do what you are doing? Well, not exactly the same, of course, but okay, why is it impossible? Some people were thinking, like Edouard de Bonnery that you were quoting, thinking that Google Calico was making a lot of tests on mice. It seems to be not true. Okay, so that's the first part of my question. And the second part is kind of similar. Why is it impossible to have public authorities using this absolutely symbolic amount of money for them?
All right. So
yeah, that's my questions.
Right. So let me go through these entities one at a time. So first of all, Calico. I don't actually know what Calico are doing. Nobody really knows what Calico are doing. But certainly I have no information to the effect that they are doing really big lifespan experiments in mice. However, that's a shame, because I basically tried to embarrass Cynthia Kenyon into doing big lifespan experiments in mice because of things that she said publicly a long time ago. Honestly, if they're not happening, then my interpretation is that she never really believed what she herself was saying. But about the possibility of getting really big lifespan extension in mice by doing genetic screens. But I could be wrong, so we hope for the best, but that's all we can do because Calico have a very clear policy of basically not telling anybody what they're doing, which is appalling and disgraceful, and it's not Art Levinson's fault, it's not David Botstein's fault, it's not Cynthia Kane's fault, it's Larry and Sergey's fault, and I think it's disgraceful. Because they don't need the money. Calico is officially a company, but they pride themselves on having a long-term view. They don't have any ambition of making money this way in the even the medium future. So there's no excuse. It's absolutely disgraceful. Altos, I am suspending judgment on Altos. I'm hoping for the best. Altos is, of course, a very new company, a very young company, and I think that Jeff Bezos, honestly, is a lot more focused on aging than Larry and Sergey are, and certainly Yuri Milner is. So it's got a chance. The other thing that gives it a big chance is the fact that they have hired so many really good scientists at the beginning of the project, which, of course, Calico more or less decided on their policy before they had done that. They hired like David Botstein and Cynthia Kenyon, and that was that. And after that, it was just, there was nothing that could be done. I think the diversity that they have within Altos from the beginning gives a good chance that they will do good work. Also, it seems that they are not in any way being prevented from, communicating with the public. So Steve Horvath is one of the scientists that they've hired, and he is coming and speaking at my conference in August the 17th to 20th, which was announced yesterday. Manuel Serrano would come, except that it's in August, and he is from the Mediterranean, and you know what that means. That's very good news. Evolution have very distinctive problems. At the end of the day, this is money coming from someone who nobody can, we have no experience of people like that. We just have no knowledge of how to guess what's going on in their head, right? So we have the enormous good fortune that Evolution is run by probably the only person in the world who could do that job, Mahmoud Khan, who understands, the psychology of that kind of culture, who understands also how to get things done on big scale. He's a miracle. I have nothing but praise for that man. But things are going far too slowly. They say they're going to spend $1 billion a year, and I'm sure they will eventually. But what they really mean is they are going to ramp up to $1 billion a year, and how long they take to ramp up remains to be seen. So honestly, they have done some things which were, of course, as you say, symbolic. They gave like $10 million to AFAR, to the American Federation for Aging Research, to disburse in small grants. They gave $2 million to Impetus. It's pathetic, but at least it's better than nothing. And as I mentioned, I am in quite close conversation with the people at Evolution, and I'm optimistic that I can continue to have some impact on their decision making. Then with public money, well, of course, this is a problem that we have had since the dawn of time, and public money ultimately is controlled by people who have one goal in life, which is to get re-elected. And so we have to start by shifting public opinion in order to shift public policy. And of course, that's what we've been doing over all these years, and it has had a small effect. Such that now we can have organizations like the Alliance for Longevity Initiatives actually having proper conversations, meaningful conversations with people in Congress in the US. 5 years ago, they couldn't have done that. Conversations happened, of course, but they were not real conversations. They were conversations in which the elected people would be terribly polite and courteous and not pay any actual attention because they knew there were no votes in it. That is changing as time goes on, and people like myself and David Sinclair and so on start to actually get people to be more optimistic about bringing aging under medical control. It's still a long, long way to go, of course, but we just have to keep plugging away.
Okay, just one quick comment to say, once again, with public money, you even don't need normally to convince the politicians. You have also bureaucrats and so on. Yeah, that's and once again, it's so symbolic money. There are hundreds of millions for many things that are totally unuseful. But okay, and maybe if you were obliged, let's say, to put your energy in one country, you would go to the US, I suppose, and then which country or which countries?
Well, I don't really think in terms of countries. I think in terms of people. And certainly I mostly think in terms of wealthy people, because even though we are very grateful for all of the small donations that we get, whether it's at LEV Foundation or at Sense Foundation or anywhere, nevertheless, even with all the work we've done, the small grassroots donations add up to only a small minority, maybe 20% of our total income that we've been able to bring in over the years. So ultimately, the wealthy people who provide very large donations are the ones that matter the most. And when I say donations, I am focusing on that because in the private sector, where we're talking about investments, things are moving pretty well now, as I explained, better than they were anyway, a lot better. But the problem is, of course, that people who invest generally want to make money back quickly. And therefore, there is a strong bias towards the more low-hanging fruit, and the more difficult things, which are just as important, don't get done. So that's why I'm still focused on the non-profit, on the pre-investable side of things. So in terms of which countries, well, of course, a lot of the crypto billionaires that have come in recently are from the US. But let me, since most of the people here are from Russia, let me emphasize how wonderful it is to speak to a group of Russians. I love, whenever I come to Moscow, it's just a fantastic experience for me because you all have, you're all very knowledgeable and also you're all very committed, which is not what I see elsewhere. Yeah, I mean, of course, a lot of the wealth that's coming in out of crypto has come from the former Soviet Union one way or another, and I'm honestly not worried where it comes from. I just try to talk to everybody.
Thanks you. Finish for me.
Thank you, Didier. So Aubrey, how much time do we have?
I have another half an hour. I have another half an hour.
Oh, amazing. So there are two more questions in the chat. Sergey is asking, do you consider combining rapamycin with metformin to alleviate some adverse effects?
Yeah, so at the moment, we have decided not to try to combine more than one aging slowing thing, whether it's a calorie restriction mimetic or whatever, simply because that's the kind of thing that other people are already doing, like people like Brian Kennedy and so on. So, for example, probably the single best combination in terms of the actual data that's already out there is rapamycin plus acarbose. And so the ITP did some work on that, and it looks pretty good. But I agree, rapamycin plus metformin also makes a lot of sense. We might very well use acarbose in the second round of our experiment, because we like the idea of having a kind of, if you like, a non-repair control intervention, like rapamycin is for the first round, but we probably won't use more than one at a time.
All right. All right. So there are people that are raising hands right now. Timothy, I will give you a word a little bit later. I'm curious what Alexander Sviridov wants to ask here.
Thank you. Hi, Aubrey. I would like to know your opinion on the following question. Here at Open Longevity, we have quite a diverse crowd, quite a lot of people with different background, and most of them, I would say, they do not have a biological background. But what unites them is that they want to help, but they don't know how to help. And what do you think is the best way for general public to help scientists like you?
Yeah, fantastic question. So, of course, you're completely right. There are lots of people in that position. And the key thing for me is that those people are not all the same. They have different skills, right? So what should we do with that? Well, of course, the biggest thing that I have done recently in that regard is Less Death. The retreat that I seed funded last August, I think it was, run by one of my early proteges, Mark Hammerleinen. It was the most extraordinary blowout success. Essentially, that it involved maybe a dozen of the experts and people, top people in the field giving like tutorials and so on. But the audience was 50 people of exactly the sort that you just described. And those 50 people had very diverse background. A lot of them had entrepreneurial track record. They'd run and sold businesses, for example. Other people were in the media. Other people were in policy, things like that. But the point is they all had exactly what you say. Some of them had biology training up to a point, but they were definitely not professional gerontologists. But they were all really committed and wanted to do stuff, and they didn't really know how to do stuff. Obviously, over the years, I have deployed people like that occasionally here and there. When I find when I see a good opportunity for two people to work together to complement each other's skills, but that doesn't really scale. So that's why I seed funded Less Death. And it was the most extraordinary success. Literally 2/3 of the people who attended came back within the next 2 weeks when they did a survey, and said that they had already made contacts and collaborations that were concrete things leading to new initiatives. 2/3 in 2 fucking weeks. It's just unheard of, right? So of course now it's just rolling. There's going to be 4 of them this year. The second one happened last week, I think. Again, a massive success. They're going to be all over the world. So this seems to work. This really seems to work. And I would definitely encourage you, I can introduce you to Mark, so that you can discuss the possibility of trying to do a similar thing in Russia. I think that would be absolutely fantastic.
Well, we were running our schools even before that, both in Russia and in some other countries.
That's true, you were.
So, yeah, I would say that it is a successful experience. Yeah, create the media and then let people decide for themselves. And I actually went to the winter camp myself. I was a consul there.
Okay, great.
Yeah, it was a blast. It was amazing. They did just amazing experience. They managed to create this atmosphere. So yeah, that's a good example of what could be done. Timothy, what was your question?
Hello. It is really good discussion, I think, and I got a little technical questions about your experiment also, just to know what you plan to do with hematopoietic stem cells. And this question is, would you like to separate them from bone marrow, or it is different ways for separation in case of it could be separated only by CD34 marker, or in another cases, what decision?
So we put a lot of thought into this, and we decided only to go at the level of the CD34 marker. So we know that what we're getting, that one purification step, will include long-term repopulating stem cells and also short-term ones. And we're okay with that, because that's what the 2020 paper did, the one that we are pursuing. And it's also because, honestly, the technology for doing so is better. If we go the further step and we try to isolate the long-term repopulating cells, we don't really know what's going to happen. In particular, one thing that is something of a concern for us is we want to make sure that there may be other cells that are not actually HSCs. There may be MSCs, for example, that are actually in the stuff that the 2020 study injected, and they may matter. They may be important. So we want. This is where we are kind of, we are taking into account what we don't know and trying to just faithfully replicate as much as possible the published study that worked.
Okay, and the second question about you inject these cells or you make any treatments for increase the efficiency of engraftment?
Oh, sure, we do mobilization. Yeah, we do the standard mobilization protocol. Again, what this study from 2020 did, and so many other studies have done. So we inject GCSF, I think 8 times over a period of 4 days. I think that's what it is. And then there's another special chemical that was discovered not long ago, which you can inject once after you've done all the GCSF, and that greatly improves the level of mobilization and the level of engraftment. So we're doing that as well.
Okay, so it is your molecule. The second one is.
Oh no, it's not ours. It's called AMD some number. I forget the number, but it's mentioned in many papers. I can look.
Okay. Perfect. Yeah. Thank you for this explanation, because it's important. To understand your solution. Also, it is really interesting. Do you like make specific tests for understanding the health benefits related with each of interventions separately? So you told about behavioral tests, you told about tests, blood tests like glucose and what types of testing you choose for?
So I don't have all of them in my head, but we've written them down. If you go to the description of the study on the LEVF website, it describes them in some detail, and we will describe them in more detail very soon in updates on the website. But yeah, I mean, the basic thing is absolutely that we want to know which things have which effects, right? So that's why that's one of the big reasons why we are doing this timing of the testing based on the survival curve of each group independently, rather than fixing the same chronological age.
Okay, yeah, thank you. Also, it is really interesting because we're also thinking how to like improve social impact of each of that study, and the Anastasia mentioned about visualization of during the lifetime of mice, and we think that. So it is like an idea in the air that we can maybe collaborate in some cases with you, because the idea that we can make video of these mice groups could not only be the tool for behavioral study, but also can be like streamed in internet, and it is could be like a solution not only to determine the mice, and probably it is not really big difficulties to paint the nails and to determine which mice are which during experiment.
So we do have various ways to determine which mice are which. And I agree about the impact, the social impact of videos. Certainly there's a lot of that goes on, but I don't think we have to do videos of all the mice. We may perhaps be able to take individual mice that we feel are particularly useful for their age, and take videos of them, just kind of to cherry pick the most impactful things. But that wouldn't really be part of the study. We wouldn't expect to get statistically significant information out of that.
Just because we have probably good scientific expertise, and maybe Anastasia will continue me about it, about analyzing big data, also behavioral data. In a case of, I understand that you can determine which mice are which, but on the video it could be difficult, you told before, and it could be like a painting of nails. But but
it's not so much that it's difficult to determine which mice are which. It's just that if you have a cage in which there are 5 mice, then
yeah.
you don't really have a good answer. You're not really getting the impact that you want. The best thing to do is to take one mouse and show it off.
Yeah, just
can I
They're
add
not
some?
really showing their nails there.
The thing is, when we record a lot of mice, first of all, it's really easy to recognize each mice and follow it through the whole life. Because even for cells under microscope, there were developed a lot of tracking algorithms that could recognize each cell separately. And also using such big amount of mice, we can get a lot of longitudinal data. And based on that, we can probably develop different mathematical models to estimate by this movement of mice, like locomotor activity, to estimate health span and biomarker as well.
Yeah. Okay.
So,
I mean, if you think there are ways to get more information without spending too much more money, then let us talk about it in more detail. Send me an email. We might be able to discuss it with the group in Syracuse who are doing the work, and we might see whether there are other opportunities.
Yeah, great. I will send it.
Yeah, it is just a way we think we have not only the volunteers, but also scientific expertise inside Open Longevity. And we are really interested in your design of experiment because it's directly what we think is important to do nowadays. And we are ready to help in some cases of analyzing big data studies, big data, and maybe like participate in some small experiments.
We will definitely look into that. We will definitely look into that. Yeah. Well, let's talk by email and maybe have a Zoom call with the people in Syracuse at ICOR. We'll see.
Yeah. Thank you. Sure. And just the final question is is about your ideas of multi-target treatments, combination treatments. So because some scientists, and I speak with Cynthia Kinyon directly about combinational therapies and your thoughts about it, and also Petr Fedichev told me the same, that in their opinion, combinations will go to Plato. So because of all the hallmarks of aging is really connected on the second layer, it means that if you treat some of them in their vision, it could be resulted not in exponential growth of lifespan, but
honestly, I think that's probably correct when we are talking about age retardation therapies, calorie restriction mimetics, or other things that manipulate metabolism. I think that, yes, we will reach a plateau. But I don't think that applies when we are talking about damage repair.
Okay.
I also would like to because this experiment includes the acquirement of new stem cells, and so the system will change. So probably we cannot apply this model to such case. Because
Nastia, let me
will get new cells.
Nastia, let me understand what you are saying.
This is not closed system. It will change the how to say it.
Okay, Nastia, I'm not really understanding what you said. Are you talking about our use of blood stem cells?
No, yes.
Okay, so yes, it's certainly.
Yeah, I'm talking about. Timofey said that there could be such a situation that all the interventions will finally we will reach a plateau. Right, Timothy? That's what you was talking about.
Yes,
but that was described in Petr Fedichev articles, as I understand it, such model did not include cases when we change the system content. And
Right.
this action, when we add new cells to the mice, this is a significant change to the system. And this is not included in such model that was described in Peter's articles.
Okay, so it sounds like you're agreeing with me. That works?
Yeah, I'm agreeing with you. But maybe this is much more interesting to anyway get at least like 12 different blood tests by 12 like several blood tests that will include at least 10 or 12 markers.
Sure.
And that would be longitudinal, so we will get we will be able to investigate this case when we add stem cells, and how this case is different from the case that was described in Peter Fedichev's model, when mice were not perturbed by such an intervention.
Yeah, one thing I should mention, I forgot to mention earlier, the measurements of health that we are doing, the visual and behavioral and blood tests and so on, of course, some of them involve killing some of the mice, so forget about those. But the ones that do not involve killing the mice, we are doing most of those tests on all the mice that are alive. There are some very expensive ones that we can't do on all of the mice, but most of them we are. And that means that we can indeed do longitudinal stuff. In particular, it means that when we get to the end of the experiment and we just have a few mice left that have done really, really, really well, then we can look back and say, okay, how are they getting on at earlier ages? And we may be able to understand which are the more important aspects of the health of the mice that led to them living a longer time.
Yeah, and also one thing that would be also very, very cool is to do a blood test before a perturbation with blood.
Oh yeah, we're doing both. Oh yeah, we're definitely doing all of that. Yeah, we're definitely doing baseline for everything.
Thank you. Yes. Just thank you for an interesting discussion.
Pleasure.
So Joseph was going to ask something. Joseph, are you with us?
Yes.
Hi.
I have 5 or 6 questions in order of importance.
Not sure we have that much time, but yeah, pick the most important ones.
The first question is a extension of Anastasia's question earlier, where she asked, what's the most costly activity in your research? And I'm interested in, like, what's the top 3 or 4 things in that aging labs are paying money for?
Yeah. Well, aging labs in general, or in our experiments? Yes. Aging labs in general. Well, in general, it's not really. It doesn't really work quite that way, because aging labs in general, they do what they are given money to do, and so they have to write a grant application, and they have to convince people that it's actually worth funding, and a lot of that. So a lot of it is kind of self-fulfilling, it's circular arguments that you have to make a case that you are going to be spending this money terribly well, and you're likely to find things out and so on. And it's usually distorted. So certainly, if you want to experiment on older mice, then that's a big expense. But in general, this is the main reason why experiments on damage repair therapies are not done, or when they are done, they're done only on a small number of mice. And so now, even now, with this work that we're doing now, we are working on, we're combining interventions that already have lifespan data. That's great. But in all of these cases, except rapamycin, we've only got 1 or 2 studies that we're basing it on. It's pathetic. So yeah, I mean, the expense is basically the same as it is for our work. Different things just cost what they cost. But if you look at labs in general, then you're kind of asking the wrong question, because they've already predetermined what they're going to spend their money on.
Could I rephrase the question?
Sure.
What single reagent or piece of equipment would save aging as a field the most money if it was halved in price?
if it were halved?
Don't need to answer that now, but it would be nice to get a list.
Yeah, I mean,
Because I know some entrepreneurs
the way that I normally think about those, because people ask me questions along the lines of, which areas of technology are have the greatest potential for investment to improve the technology, to make the technology work better, or in many cases to make it less expensive, right? So that's kind of very closely related to your question. And honestly, I don't have good answers to that, because so often the answers come as big surprises. Like,
Yes.
Huge amounts of money is now being saved by the emergence of AlphaFold across the whole of biomedical research, right? I couldn't, if you asked me 5 years ago, I wouldn't have said, yeah, let's solve the protein folding problem, because that would have been a stupid thing to say, right? And here we are, right? So it's that kind of thing. That's why I don't really think in those terms.
Okay, I have another question then. What order of magnitude does the whole field of regenerative medicine have in terms of funding, in your opinion?
If you talk about the whole field of regenerative medicine, certainly billions.
That is your work, I mean.
I'm sorry, say again?
So distinct from just pharma research in general.
I would say still billions. If you talk about regenerative medicine as a whole, you're talking about the whole of stem cell therapy and the whole of tissue engineering, right? And that's even if you define regenerative medicine relatively narrowly, and you don't include the kind of things that I would like to include, like molecular level regeneration, getting rid of waste products and so on.
Okay, whatever you would count as aging research.
Oh, well, so that's completely different, because 90% of stem cell therapies and 90% of tissue engineering has nothing to do with aging, right? So if we talk about aging research, then again, it's billions, but the main thing, of course, is that it's very unevenly distributed, because the bulk of the money is going into relatively low-hanging fruit that can make money soon, or that some people think can make money soon. And the stuff that is pre-investable, it's an earlier stage, is still struggling. It's struggling a lot less than it was even 2 years ago, largely because of the arrival of a very small number of extremely wealthy crypto people. Really only 4 of them, Vitalik Buterin, James Fickle, Juan Benet, and Jed McCaleb. They've each put 8-digit amounts of money into the field, and they've all done it philanthropically. So that's made a huge difference. But we definitely need more of that. We were able to scrape together enough money to start this $3 million experiment. We want to do another one in October, and we've only got half the money for that at this point.
So would you say it's in tens or hundreds of billions?
So one thing that, in order to answer that question, I have to remind everybody of one thing that I've always made clear, which is that the early stages of this research are vastly less expensive than the later stages, but they're also vastly more difficult to get the money for, because of the lack of de-risking, so to speak, right?
Yeah.
And so I would say that at this point, we are still looking at in the region of $100 million a year, 100 million, not billion, $1 million a year, as the thing that would completely change the game, if it were all allocated to the pre-investable area. Because once it is, things get to be investable at a rate that is limited only by the difficulty of the science. And as soon as that happens, the billions and the tens of billions and the hundreds of billions fall out of trees.
Okay, next question, if you have time.
Sure.
Some years ago, Senzarov commissioned several animations about certain aging mechanisms. I've got 6 links here, and I'm not sure if I should share them. So I want to know, why were they hidden?
Carelessness. There's nothing wrong with them.
Okay, their knowledge in those animations isn't incorrect now, or?
I'm not aware of anything incorrect in any of those animations.
Okay, thank you. And hyperbaric treatment or high oxygen ratio treatment. does it do more damage than it does help?
Great question. Yeah, honestly, I haven't studied it well enough to know, and I don't think anybody has. I think at this point we've got, anecdotal and perhaps, preliminary studies on this, but I don't think we can draw conclusions yet.
So specifically, I'm concerned about oxidative damage inside blood vessels.
Well, of course, yeah, that's right. Yeah, that would be the obvious thing to be concerned about.
Stroke damage or heart attack damage, which it
yeah, we don't know. We honestly just can't say. I mean, we have to remember that oxidation, the free radical generation by the respiratory chain is a very complicated process that is not necessarily linearly related to oxygen tension. And also, of course, oxygen doesn't necessarily just rise proportionately across tissues, like cells that have very low oxygen tension because they're not right next to blood vessels may continue to have relatively low oxygen tension even in hyperbaric context. These are questions, as far as I know, that have simply not been studied in sufficient detail for us to draw any conclusions.
About government or political-based funding, there's starting to be some whispers and murmurs about an aging population crisis, and how that's going to, or the demographic crisis and so on. What approaches have you taken, or others taken, to sort of dangle the fruit in front of governments to get early stage research money?
Yeah, it's such a joke, isn't it? I mean, of course, when you say starting, you're completely wrong. This has been a conversation for decades. And it's getting more intense, especially in certain places like Japan. But yeah, sure. But of course, at the end of the day, people look at the range of potential solutions, and they're only interested in the solutions that they think are possible. So everyone's still focused on increasing the birth rate. I mean, come on. I mean, for crying out loud. Because of course, everything that's been tried to increase the birth rate anywhere in the world has been unsuccessful.
I don't want to get political. I just wondered about, can it be used to incentivize funding?
Well, so of course the point is that if we could persuade governments that actually there was some likelihood that investing a sensible amount of money, like in the billions, in aging research would actually deliver results, would actually postpone the health problems of late life, then we're done. Because absolutely, they already accept completely the argument that even a very modest postponement of the health problems of late life would be just astronomically beneficial economically and, of course, demographically. Therefore, the only problem is that they think it's a pipe dream. So, we just have to fix that. We have to make sure that that they understand that actually you can no longer say it's a pipe dream. We are within striking distance. And that takes a bit more courage on the part of a few more experts, and we'll be there.
Okay. Next question is, has there been any progress in standardizing a benchmark for aging reversal or aging damage?
No, but that's okay. That's a kind of okay, because what we already have really is okay. I mean, it's less okay at early points in life, where you have to rely on very proxy measures. Of course, epigenetic clocks are very fashionable these days, but everybody understands that they've got a long way to go to be accurately predictive. But
just to clarify, when you say what we have, is that the checkup you do every 5 years or something?
I mean a bunch of things. So I get checks done on myself every few years, which are pretty high end, measure 150 different things in my blood and cognitive stuff and so on. But actually, I'm also talking about the functional things that have been studied under the general heading of activities of daily living. So, I'm particularly fond of the work done by Ken Rockwood and Arthur Mitnitsky in Canada, but that's just really one group that's done this. They look at the predictive value of how many of these standard things you can do. And so people progressively lose the ability to do this and then that and so on. And they lose them in different people will lose them in a different order. But that's kind of okay. It's still the number you've lost is still predictive of how long you're going to stay healthy, how long you're going to live. And it's remarkably accurate, that prediction. So, basic things like this. And of course, other equally basic things like grip strength and gait speed. These are really quite good.
Thank you. Final question. So I've sort of imagined that there's like the closest treatments. There's like a set of closest treatments that, when put together, will be convincing to the public and unlock all of this funding that we need. My list here is senolytics, stem cell reseeding or some other cell replacement, and cancer reduction or prevention. And you've answered a few questions, but would you give a different list? Is it more than 3?
Oh yeah, I mean, you know my standard list of 7, right? Yeah, I mean that's my.
And which are enough to like make a big difference?
I don't know. So I'm a bit more optimistic about that, at least in mice, than I used to be. Back in 2011, when we saw the first experiments on removal of senescent cells, which of course were not done with senolytics, they were done with genetically clever, models. I think everybody was blown away. I certainly was, by how widespread were the beneficial effects. People had been thinking, certainly, way back when Judy Campisi came up with the whole idea of senescent cells being actively toxic, her vision of it, and mine as well, was that the toxicity would be limited to the pro-cancerous effect on neighboring cells, close-by cells, like really a paracrine effect, right? And it turned out that was nonsense. It turns out that the SASP, the senescence-associated secretory phenotype, it's really nasty and really pervasive. So that was a big surprise. And what it means is that we can probably get away, at least in mice, with a more incompletely comprehensive panel of interventions to get a given amount of postponement of aging than what I would previously have expected. However, we don't know how general that phenomenon is. Essentially, what it is, we're getting a quantification of the amount of crosstalk between the different types of damage, right? And we don't know how much that crosstalk is going to be for other ones. We don't know how much it's going to be in humans. So at this point, I'm not I'm not getting too emotionally invested in. Yeah, I'm still up for trying to fix all of these things fairly well.
Yeah, of course.
And I've got 2 minutes.
Joseph, you have 2 minutes, right? Aubrey, you said you have 2 minutes?
Yeah.
Okay. Joseph, thank you for circling it back to the combinational topic we had initially. Quick question. Aubrey, how do we make this whole combination research into competition? Into friendly competition, or maybe not so friendly? I
this could be a potential, to grow the field.
Well, first of all, I think let's absolutely make it friendly. I think that a huge part of how the field has got as far as it has is because of the friendliness, the collegiality. In fact, I pointed this out yesterday. Somebody or other highlighted, yes, it was Michael Grieve, wrote a tweet saying, talking about the piece that Reason from Fight Aging had written about Cyclarity, one of the Sense Research Foundation spin-out companies. Now, I pointed out that this was fantastic for a whole bunch of reasons, but especially because Reason is also the CEO of Cyclarity's main competitor, right? They're both working on, ways to get rid of oxidized cholesterol. And so, you wouldn't see this in any other discipline, right? And we have to maintain that. So I believe that, we will maintain it. I think if Evolution can be persuaded to put proper money behind a consortium to do combination therapies, that will be transformative. And so I'm going to be working very hard to make that happen. But yeah, that's the way we need to go.
All right. So, but what about competition?
You can have competition at many levels, right? I mean, for example, we might have a little sweepstake within our experiment. So people can bet on different mice living the longest, things like that.
Yeah, like that. Yeah.
I don't have any problem with that gamification type thing, but I think it's not really what I would call competition.
Or hackathon or something like that. Yeah.
Yeah, all that.
Mm-hmm. Mm-hmm. All right, we probably need to let you go now because you give us.
I know that other people.
2 hours of your time.
I know other people. Yeah, it has been right. It's been a fantastic tour. I've really enjoyed it. I know other people have still got questions. My email address I'm putting in the chat right now in case anyone doesn't have it.
And we'll also collect all the unanswered questions, and maybe we'll try to do some follow-up or something like
Yeah,
that.
absolutely. Anyone can email me. I
Or
sent
you.
that. I
You good?
didn't send that to everybody. Hang on, let me send it to everyone. Bang, bang, bang. There we go. Okay, that's my email address. Anyone can email
Fantastic.
me, and I'll be delighted to continue any of these conversations. All right, gotta go. Bye-bye, everybody. Thanks again.
Thank you, Aubrey. Thank you.
Thank you.
John,
Thank you.
Great.
and all the other guys.